Okay, good afternoon class. So today we're looking at number patterns. So we're looking at the example on page 76. And this is the examples of for exercise 7.4 on page 77. Okay. So now we look at geometric patterns of a quadratic sequence. A number that can be represented as a number of dots in a triangular array is called a triangular number. Okay. You get the pentagonal numbers, you get triangular numbers, and there's another one, octagonal numbers, I think. But there's more than that. Okay. But these numbers, if you didn't learn it in grade 8 and 9 or 10, there's actually a way of doing that using what we have just learned in our previous lesson, which is your quadratic patterns. Okay. So your geometric patterns, basically they give you a shape or a pattern or a sequence, as you can see here with dots. Then you must translate or transfer those dots to numbers. You understand? So if you're looking at the first thing, the question says in stage 1 we have 1 dot, in stage 2 we have 3 dots, in stage 3 we have 6 dots. So what I do is, whenever I given a pattern like this, I translate this to numbers. So that is 1, then 3, then 6, then 10. If I extend this, then what am I going to have? 15 dots, and so on. Okay, you guys understand? Now it is determine the general term of the sequence generated by the number of dots in any triangle in terms of the stage number. Okay. So in other words, the nth term is what they want you to calculate. You guys understand? Is there anybody that's confused? Alright. So where do we start, people? We start by finding the first difference. Now we move from 1 to 3. You're adding 2. Then 3. Then 4. Then 5. You guys understand? Is there a first constant difference? No. The first difference is not constant. This is not all the same value. So it doesn't have a constant first difference. If it had a constant first difference, it would have then been an arithmetic progression. Not so. Okay? But it doesn't, so we find the first difference here. So that is 1. Then. So it has a second common difference. So if it has a second common difference, what is this then? Quadratic. So now I want you guys quickly to determine the nth term of this progression. Okay, the nth term of that progression. Right, so what do I write on the side? 2a, then 3a plus b, then a plus b plus the bottom up. Okay. So what do I write? 2a is equal to 1. So a is equal to, then what do I say? Then say 3 into plus b is equal to 2. So b is equal to 2 minus 3 over 2, which is also half. Not so? And then we have half plus c is equal to 1. So that gives us 1. So c is 0. So I can determine my general term. I can define it as Tn. Therefore Tn is equal to a half n squared plus half. And what do I do? I always test. So this test, this user n value of 5. This is go half times 5 squared plus a half times 5. And the fifth term is equal to 1, 2, 3, 4. The fifth term is 15. That is equal, and 15 is correct, which makes that my general term. Will you guys understand? Okay, so with that, you should be able to do exercise 3.4. Okay, which also brings us to the end of this chapter. Okay.